So now we have given the definition of the Hadamard matrices. And the natural question to ask is that for which n does a Hadamard matrix of n by n exist? The case when n is equal to 1 is really trivial. For n equal to 2, you can look at the following matrix. Matrix A, that is 1, 1, negative 1, 1. The determinant of A will be equal to 2, which is 2 raised to the power 2 divided by 2. So, by this equivalent thing, you know A is a Hadamard matrix. Now what happens when A is greater than 2? As a matter of fact, we have the following theorem. For n greater than 2, if an n by n matrix is Hadamard, then n is a multiple of 4. Now let's prove this. Now suppose A is n by n Hadamard matrix with n greater than 2. Now we write as before A as a block matrix where each block is a column. Now we make an observation. We observe that the multiplication of any row or column for A by negative 1 will not change the equation that ATA and the AAT are both equal to the scalar matrix n times In. This is easy to check. Say, if we change the column A1 to negative A1, then the resulting matrix A prime is negative A1, A2, all the way to AN, and A prime transpose times A prime is equal to and the entries here are AIT, AJ, plus minus but you know that those off-diagonal entries are already 0. So this must be equal to the original AT times A, which is n times I. Now if A prime t times A prime is equal to n times In, you know from linear algebra that if you flip this product, you will still get the same thing. Because A prime is a square matrix, this equation shows that the inverse of A prime t is A prime divided by n. So if you flip them, you get the same thing. So you can also check the situation when you change the row to to the negation of that row, and the argument is the same. So that verifies this observation. Now, what does this observation tell us? The observation tells us, without loss of generality, we may assume that the first column of A are all ones. If they are negative ones, we'll just multiply the row by -1. This is just the beginning. And here comes the tricky part. Now, since A is Hadamard, we know from this property number B that A1 transpose times AI must be equal to 0 for any I greater than equal to 2, less than or equal to n. You can also check it with our computation here. The off-diagonal entries are all equal to 0. So in particular, those n-1 entries are equal to 0. Good. But we have assumed that A1 has its entries all equal to 1. What does this tell us about A sub I? We know from this and this that each A sub I, where I is from 2 to n, must contain exactly half of n many ones and half of n many negative ones. And in particular, n must be even. So this is one step closer to what we want to prove. Recall that we want to prove that n is a multiple of 4. Now we have shown that n is a multiple of 2. That's good. And now it comes to the trickiest part. Now let's look at the columns A2 and A3 of A. Now for this given A, we consider the following 4 numbers. They are cardinalities of 4 sets. So what we are doing here is that we are partitioning the n-element set consisting of the pairs A12, A13, A22, A23, all the way to AN2, AN3 into 4 sets based on this pair AI2, AI3 is 1, 1, 1, -1, -1, 1, or -1, -1. So there will be 4 categories. This is a partition of the n-element set. Let us call this the equation number 1. Our next goal is that we're going to find more relations for A, B, C, and D. So now let's find more relations between A, B, C, and D. Since A1t times A2, which is the inner product between vectors A1 and A2, is equal to 0. Here we are using these relations, this orthogonality condition. Because this is 0, now you compare it with our construction, you will see that we have A plus B and C plus D are both equal to half of it. Because here A plus B counts the number of AI2s that are equal to 1. And C plus D counts the total number of AI2s that are equal to -1. In order to make this inner product to be 0, they both have to be equal to half of it. And let us denote this by equation number 2. And similarly, since A1 transpose times A3, which is A1 and A3's inner product, is also equal to 0, we have A plus C and B plus D are both equal to half of it. This is because A plus C counts the number of A13's that are equal to 1. And B plus D counts the number of A13's that are equal to -1. In order to make this inner product to be 0, they must be equal to half of it, so that you get 0 inner product. They cancel out. Now, the equation 2 and equation 3 together will give us, because A plus C is equal to A plus B, B must be equal to C. And because B is equal to C, we can cancel B and C here and get A equal to D. Now, we further observe that since A2t and A3's product, which is the inner product between A2 and A3, is also 0. This relation tells us that A plus D must be equal to B plus C. Because when you take this inner product, A plus D counts the number of plus ones, and B plus C counts the number of negative ones. Because in the situations A or D is 1 times 1, -1 times 1. And in the situation B or C is 1 times -1, -1 times 1. So in order to make sure they cancel out and give us 0, A plus D must be equal to B plus C. So now because A is equal to D, B is equal to C. Now we have A equal to B equal to C equal to D. And because their sum is equal to n, they must all equal to n divided by 4. And in particular, gives us 4 divides n. This guy must be an integer. And this finishes the proof of this theorem.